Welcome to this seminar from Lancaster University. This is the latest in a series of seminars around developments in materials science in conjunction with the European Regional Development Fund project GISMO, which stands for Greater Optimisation for Smarter Materials Optimisation. I'm Alex Robson, an Innovation Fellow on the GISMO programme, and I'm delighted to be introducing the seminar today by Alessio Quadrelli, one of the graduate researchers funded through the GISMO programme on nanoscale polymers for surface functionalisation. Just as some brief housekeeping notes, the seminar itself will last for approximately 30 minutes. It'll start with a brief introduction to the Materials Science Institute at Lancaster University, which the GISMO programme is linked to, and we'll also briefly talk about the research groups that Alessio works in. Alessio will then give his seminar, and we'll have some time for questions and answers at the end. And after, we'll briefly speak about the GISMO programme and the ways you can engage with us. Could I ensure that all your cameras and microphones are turned off if you're joining throughout? And if you have any questions or comments through the seminar today, please write them in the chat box and we'll address them at the end of the presentation. So just very briefly, Lancaster University's Materials Science Institute. So it's an institute of over 200 academic and research staff, active in interdisciplinary research, development, commercialisation and education of new materials science, with an aim to provide a platform offering solutions to research and development needs. It's cross-departmental and cross-faculty, and it aligns to national roadmaps for materials and manufacturing, with goals around facilitating new knowledge and innovation in materials science and engineering, improving models of industry engagement and providing greater opportunities for commercialisation and spin-out activities, facilitating transformational change in manufacturing practice, and improvement in well-being and quality of life. And it has dedicated links into Lancaster's Health Innovation Campus. As to the MSI's strategic focus, well, researchers are aligned to core areas to tackle problems in industry and society. Broadly, those areas are active surfaces and interfaces, where we work to understand and engineer how materials interact through their surfaces and interfaces. Health innovation materials, with researchers developing new materials to solve problems in healthcare and medicine. Advanced manufacturing, so developing advanced techniques to fabricate and join new materials to make next generation technologies. And materials social futures, so designing new materials and technological breakthroughs for better societies and a healthier environment. Basically finding ways to bring the benefits of materials science together with better understanding of social and human values. And Lancaster's MSI researchers have access to cutting-edge facilities and unique lab environments across the university. We've been very fortunate in the last decade to have heavy investment in departments and facilities across the university. So Alessio works across two research groups. His primary supervisor is Dr. Sam Jarvis, who works in the physics department. Originally, Sam would have given this introduction today, but unfortunately he's not able to attend. He has provided a number of slides about his research, so in his absence I'll give a brief overview of those areas, and also of Rob Short's group, Alessio's second supervisor. So Sam's research group focuses on single atom chemistry and atomically precise molecular thin films. Broadly, this can be broken down into a number of areas. So for molecular thin films, they look into fundamental studies of directed self-assembly onto surfaces, 2D molecular surface networks for things like catalysis and selectivity, applications in thermoelectric thin films, and links into plasma polymerisation, which also links up to Rob Short's group. In terms of single atom chemistry, it's looking into on-surface chemistry and single atom catalysis, as well as fundamental studies of molecular absorption and development of 2D covalent organic frameworks. And the group specialises in ultra-high resolution imaging and characterisation, so down to the sub-nanometer scale, atomic resolution imaging with ambient environment scanning probe microscopes, doing things like single bond chemical mapping and multi-frequency simultaneous characterization. You can see the people here in Sam's research group, and here's some of the bits of equipment they use as well. So on the whole, things like atomic force microscopes, scanning tunneling microscopes, ultra-high vacuum deposition equipment, and X-ray photoelectron spectroscopy. Alessio will be talking about a number of these techniques in his presentation. And they also work out of the ISOLAB facility at Lancaster University, which is an ultra-quiet facility. Within that environment, there are 3 pods tied to research groups. Sam is the head of the nanoscale microscopy pod, which is a dedicated lab with atomic force microscopes, scanning tunneling microscopes, and ultra-high vacuum facilities. This building and the pods within are designed to reduce noise from measurements. So it's got a floating floor, acoustic and electrical isolation, Faraday cages, dedicated filtered power, and remote operation facilities as well. On the other side of Alessio's research, he works with Rob Short, who specialises in a number of plasma techniques, including plasma polymerisation and plasma jets, with applications in antimicrobial and anti-biofilm spaces, interested in microplastics, their implications and degradation, as well as surface chemistry and analysis. And so at this point, I'd like to introduce Alessio Quadrelli to give his presentation on nanoscale polymers for surface functionalisation. So Alessio, if you could share your presentation, and we'll begin when you're ready.
Yeah. Okay, can you see it and hear me?
Yes, that looks fine, Alessio. Thanks.
Okay, so first of all, thank you everyone for attending. I'm Alessio Quadrelli, and today I will introduce you to my research on nanoscale polymers for surface functionalisation. I'd like to thank my supervisor, Dr. Samuel Jarvis, Professor Rob Short, and Alex for introducing me, and acknowledging Lancaster University and the European Regional Development Fund for funding my PhD. As we said at the beginning, you can pop the question in the chat and I will answer them at the end. And during the presentation, I will ask you to guess some numbers. So even at the case, you can try to pop the numbers in the chat. So the first few nanometers of a material are the surface of the material itself. And through the surface, the material interacts with the surrounding environment. In a way, you can think of the surface as the skin of a material. And in the same way as, for example, we wear waterproof coats on our skin to protect it from water, we can coat the surfaces with layers of organic molecules. This can enhance the surface properties or bestow new properties to the surface itself. And furthermore, this enhances the value of the product. Just now, quickly in the chat, can you guess what is the value of surface engineering and coatings in the UK? Okay, I can see 5 billion, 1 billion. Okay, the order of magnitude is actually right. We are talking about 11 billion pounds per year, underpinning product worth 140 billion pounds per year. In my research, I'm dealing among all the possible coating with nanoscale polymeric coatings. Polymers are macromolecules made of monomers, repeated units that are linked by covalent bond. This makes the polymer extremely stable and thus suitable for real-life application. For example, polymer can survive water environment or high temperature. Furthermore, the polymers are made of organic molecules, the monomers, that can be easily or relatively easy tweaked to achieve the desired property. And furthermore, at the nanoscale, the quantum properties of molecule emerge and can thus be used to functionalize the surfaces. Now, today, I would like to introduce you to the surface characterization technique needed to study this polymer that are available in Lancaster University, which are the AFM and the XPS, and show you some example of my research, so catalyzing on surface polymerization of halogenated monomers, and the tempoplasma polymerization for anti-biofouling, and finally the ongoing research on the antiviral plasma polymers. Keep in mind that this is a very interdisciplinary research, and I will guide you through it with the eye of a physicist. Okay, so let's start with the characterization technique. The first one is the atomic force microscopy, AFM. It consists of measuring the interaction at the atomic scale between a tiny tip and a surface, so that the surface morphology can be reconstructed and we can measure the polymer height and adhesion to a surface. As Alex said before, in Lancaster University, we have a specially designed lab called the ISOLAB, where the AFM is screened from electric, vibrational, and thermal noise, and very high resolution can be achieved. Just to give you an example, just behind the ISOLAB, there is the M60 highway, and if a truck is passing on the highway, the vibration of the AFM will be lower than the atomic scale, so 10 to the minus 10 meters. For this reason, very high resolution can be achieved. Now here I highlighted a single molecule where even the lobes of the molecule can be resolved. The other characterization technique I use is the X-ray photoelectron spectroscopy, or XPS. This technique enables to measure the chemistry of the first 8 to 10 nanometer of a surface. It consists of shining X-ray on a material so that electrons are emitted, and then measuring the energy of the electron. What you get is this kind of spectrum you can see here, when you have the binding energy and the number of counts, and some peaks appear in the spectrum. Then we can assign each peak to an element in the material. For example, you can see carbon, nitrogen, and then oxygen. Also, we can zoom in a single peak, for example, the nitrogen 1s peak, to detect subtle changes in the energy of the electrons that are associated with bonding environments. However, XPS is confined just to the first 8 to 10 nanometers. However, we can mill through the surface, so measure a layer, mill through the layer, measure the next layer, and so on, so that we can actually measure the chemistry of the whole sample as a function of the thickness. Now, actually, I'm trying to will go on with my research. So the first part is catalyzing on surface polymerization of halogenated monomers. You may all have heard of 2D inorganic materials such as graphene. These materials are extremely interesting because of their two-dimensional nature that results in very high conductivity or strength. In my research, I'm dealing with two-dimensional polymer, which share the same two-dimensional nature and so the same astonishing properties. But they are made of organic molecules, which on one hand make it easy to tune their properties, but on the other hand make them more difficult to grow. Specifically, I'm using halogenated monomers. So monomers that have a carbon-halogen bond, such as carbon-bromine, carbon-iodine, or carbon-fluorine. And I deposit them on noble metal surfaces that have two purposes. First, the surface confines the monomer into dimension, and second, it catalyzes the carbon-halogen bond cleavage, so that the monomers become radical and can then polymerize into polymers. However, as you can see, the noble metal surface has two purposes: confines the monomer and catalyze the polymerization. And in my research, I'm trying to decouple this process, so that we have three main characters. We have an inert surfaces, so a surface that's just confining the monomer into a molecule, and a catalyst. As inert surfaces, I use mica, which is an atomically flat insulator, and HOPG, which is zero band gap semiconductor, because that's technologically relevant. Second, we need a molecule. And I'm actually using the molecule I showed you before, called the bromophenyl porphyrin. This is a model polymer because it has 4 carbon-bromine bonds. I can thus form two-dimensional square lattice. And porphyrin can host in the middle metal atoms that are catalytically active. And finally, we have the last character, the catalyst. We have a very special one called the CO5. CO5 are clusters made of just 5 copper atoms. And for this reason, they exhibit an atomic nature, so discrete energy level. But they also are catalytically extremely active because the coordination number of each copper atom is very low. And they actually have been used for hydrogen evolution reaction, for example. But the interesting properties is that the CO5 do not agglomerate together, so they always remain CO5 and can thus be used for the polymerization. Now, we have all the ingredients, the surface, the molecule, and the catalyst. And the question is, can the CO5 catalyze the bromophenil porphyrin polymerization? To answer this question, first, I deposit the CO5 on a surface. And here you can see an AFM scan of the surface being highlighted in blue and the CO5 being highlighted with the orange color. Then we transfer this sample into an ultra-high vacuum chamber, where the pressure is 10 to the 12 times lower than the atmospheric pressure, so that the highest purity can be achieved. And then we deposit the bromophenil porphyrin on the surface. Now here you can see a scan of the CO5 plus the bromophenil porphyrin on the surface itself. And the question is, can the CO5 catalyze the bromophenil porphyrin polymerization? As catalyzing a reaction involves chemistry, we have a suitable tool to study, which is the XPS. So in figure A, you can see some measurement, XPS measurement, where on the x-axis, we have the binding energies of the electrons on the 2p orbitals of bromine atoms. And on the y-axis, we have the temperature of the substrate. So we are heating up the substrate to induce the polymerization. So then we have a color scale. Blue means that there is no peak in the spectrum, while red means that there is a peak. So as you can see, the peak disappears around 225 degrees Celsius, meaning that the bromine has left the surface, so the carbon-bromine bond must have been broken. In figure B, you can see what happens when there are, at the same time on the surface, the catalyst, the CO5, and the molecule, the bromophenil porphyrin. Again, we see the peak disappearing, but this time at lower temperature, around 100 degrees Celsius, meaning that the CO5 are catalyzing the polymerization. But then I wanted to actually image the polymer. So in figure A, you can see an AFM scan of the CO5 plus the bromophenil porphyrin on a mica surface. And in figure B, you can see what happened after this has been annealed at 300 degrees Celsius. We can see the formation of this orange island, which is the polymer. The same results were replicated on HOPG and even gold 111. So this is the first time that extrinsic catalyst has been used to induce two-dimensional polymerization on inert surfaces. And next, I would like to answer the question if this approach is universal. So can the CO5 be used to catalyze polymerization of different molecules, such as these phenylbenzenes terminated by bromine or iodine? Okay, so now I would like to introduce you to the research on plasma polymerization, starting with TEMPO and anti-biofouling molecules. So biofouling means the attachment of proteins, viruses, bacteria, cells, or living organisms to surface, and this can cause infection. Worldwide, we spend $8.3 trillion per year in healthcare. Can you guess how much of that expense is due to biofouling? You can try to answer it, popping it in the chat. Okay, I can see no answer. So I can tell you, it's around 5% of the whole healthcare expenses. We are talking about $0.4 trillion per year. The fact is that once bacteria reach a surface, they start growing, forming an organized community called the biofilm. And the biofilm is protected by a polymeric matrix, which make it extremely difficult to eradicate. So most of the biofilm actually have antibiotic resistance. But we have an allied against this biofilm. It's called the nitric oxide. Nitric oxide is a gas that can mess up with quorum sensing of bacteria. This can cause dispersion of already formed bacteria colonies or can inhibit the formation of the colonies themselves. There are several NO-releasing drugs and coatings. However, they're limited by complexity and cost. But the point is that nitric oxide is extremely reactive, so it is extremely short-lived. Scientists have discovered other molecules which have similar properties. One of them is TEMPO. TEMPO is a nitric oxide radical, so has an NO functional group like the nitric oxide. But this time there are 4 methyls groups, 2 at the left and 2 at the side, that protects it, make it stable due to steric hindrance. Actually, TEMPO has anti-biofouling activities. You can see in figure 1a, the bacteria, which is the green spots on a surface, which is the black part, and the same bacteria after being exposed to a solution of TEMPO in water. Now, bacteria has left the surface. So TEMPO is an extremely interesting molecule, but we cannot coat the surface with it because it has no carbon double bond, so it cannot undergo radical polymerization. However, we have a technique called plasma polymerization. This technique can be used to polymerize even saturated molecules like TEMPO. So it consists of basically a borosilicate tube that is filled with the gas of the monomer, so in this case TEMPO gas, and with an electric field we create a plasma, so that if a sample is placed in the plasma, it will be completely coated by the molecule, in this case TEMPO. Some of the advantage of plasma polymerization is the fact that the polymerization can be performed on a wide variety of substrate, ranging from silicone, glass, but even paper or even tissue or cloth. It is a clean technique as it is inherently energy and material efficient. And finally, it is scalable, meaning that the dimension of the substrate to coat is just limited by the dimension of the reactor itself. And actually, in literature, you can find evidence of TEMPO plasma polymerization. In figure control, you can see a silicon wafer being completely colonized by bacteria, and bacteria adhering to a surface are highlighted in this green color. Then in the next figure, you can see a silicon wafer being coated by a TEMPO plasma polymer, and again test for the bacterial lesion. Now you can see only tiny green spots, meaning that very few bacteria are adhering to a surface. Most of them are highlighted by this orange-yellow color, meaning that they are not attached to the surface. So actually, TEMPO exhibits anti-biofouling activity when it is several micrometer thick. In my research, I'm trying to understand how the substrate affect the chemistry and the morphologies of this TEMPO coating. To do so, I need to reduce the thickness down to few nanometers. And in this slide, you can see the results. So in figure B, C, and D, you can see some TEMPO being highlighted in this brown yellow color on different surfaces highlighted in blue. Silicon oxide, graphite, and gold. And you can see very different morphologies in figure B, C, and D. So actually, the morphology is surface dependent when the polymer is very, very thin. And in figure A, there is the N1S spectrum. So we're looking at the bonding environment of the nitrogen atom of TEMPO, and you can see different environments depending on the surface. Then I deposited the polymer for a much longer time, 10 minutes, and now they are 30 nanometer thick, and you can see in figure J, K, and L some AFM scan. Now they all look the same, they have the same morphology. Then I checked them with the XPS, and you can see in figure I that actually the N1S spectrum, so the nitrogen bonding environment, are all the same. So the growth is actually surface agnostic. So TEMPO plasma polymerization can be used to coat TEMPO, a well-known anti-biofouling agent, on surfaces. I noticed that TEMPO polymers are affected by the surface only in the early stages of plasma polymerization. And when they are 30 nanometer thick, then the growth becomes surface independent. The next step of the research would be to test this 30 nanometer thick coating for anti-biofouling activity, because if they actually exhibit any biofouling activity, we can massively reduce the amount of energy and material used with respect to the micrometer thick coatings reported in literature. Okay, now there is the last bit of the ongoing research on plasma, on antiviral plasma polymers. Now, after almost 3 years of pandemic, everyone is familiar with COVID-19. You all know that it can spread through the air, through the aerosol, and that when the drops of saliva reach the surfaces with the virus can stay alive and be infective when it is on the surfaces. You can prevent it from contaminating other people by disinfecting the surface. However, if you think about healthcare settings, it is unfeasible to clean each surface every day, several times per day. So in our research group, we prepared some antiviral contact killing coatings using well-proven antiviral molecules. Idea is that they should kill COVID once it reaches the surface. Again, to prepare them, we used plasma polymerization because we can coat a wide variety of substrate. All our tests have been performed on silicon and glass, but in principle, we can coat with the same molecule, plastic or paper or tissue, whatever. Also, plasma polymerization is scalable, so you can scale up the coating by increasing the dimension of the reactor. And finally, it is a green technique, so it is inherently energy and material efficient. In this research, we are comparing two different configurations called the single layer coating and the double layer coatings. In the single layer coatings, the substrate had been coated by a layer of antiviral plasma polymer. While in the double layer, first we coated the substrate with a layer of non-antiviral plasma polymers, and on top of this layer, we deposited the same antiviral plasma polymer. And we tested them against COVID-19. Actually, they are all effective against COVID-19, but interestingly, the double layer is more effective at 4 degrees Celsius with respect to the single layer. We're trying to understand why, because we found out why maybe we can improve the properties of these coatings to be even more antiviral. First, we check the chemistry, but we noticed that the chemistry is exactly the same, so it cannot be responsible for these new properties. So then we try to look at the physical properties. Maybe one of them is correlated to antiviral activity. To do so, we use a special AFM mode called colloidal probe AFM. This time, instead of using a tiny tip, we use a micrometer large tip to sense the interaction between the tip and the surface as a function of the distance between the tip and the surface. What you get is a spectrum like the force versus the distance that you can see in the slide. So if we start at 500 nanometers, you can see that the force is 0, meaning that when the tip is far away from the surface, they're not interacting. However, around 230 nanometers, you can see that the force becomes negative, meaning that actually the tip is attracted to the surface. Then, as we try to move the tip closer to the surface, the force decreases until it crosses the 0 line. At this point, the tip is actually touching the coating, and we are squeezing the coating. And from this part of the first curve, we can measure the mechanical response of coating to the stress applied by the tip. I prepared some sample holder for the AFM to perform this kind of measurement at 4 degrees Celsius, 22 degrees Celsius, and 37 degrees Celsius in water environment to replicate the antiviral testing environment. So, and here you can see the results. So in the first graph, there is a single layer. If we start for the first curve at 37 degrees Celsius, we can see that the force is just 0 and then ramps up, meaning that actually there is no interaction between the tip and the coating. So at 37 degrees Celsius, the coating is hydrophobic. Then as the temperature drops to 22 and 4 degrees Celsius, you can see that a minimum of the force is appearing, meaning that actually the coating becomes hydrophobic and now is interacting with the tip. We notice the same happens in the double layer, but we saw also some change in the mechanical response. And we are trying to replicate these experiments to see these results are consistent. But the key point is that with the colloidal probe AFM, we can sense the change of interaction as a function of temperature in these coatings. So just to briefly sum up, in our research group, we prepare some antiviral contact killing coatings in a single layer and double layer configuration. And they're all effective against COVID-19, but the double layer is more effective at 4 degrees Celsius, and we're trying to understand why. We use some AFM measurement in liquid at different temperature to sense the interaction with the surface, and we could actually see a change in interaction as a function of temperature, but we couldn't spot for now any difference between the single layer and double layer configuration, but this is ongoing research, so hopefully we can find something. Just to conclude, so the surface determines the interaction of a material with the surrounding environment, and we can coat a surface to enhance its performances and add value to the material itself. I show you how polymeric coatings can be used for real-life applications such as catalysis, anti-biofouling, and antiviral activities. And I show you the surface analysis technique available at Lancaster University, the AFM and the XPS, that are suitable to study these kind of coatings. So first of all, I would like to thank you for your attention, and now I'm happy to take any question. If you want to contact me, you can do so at my email, a.quadrelli@lancaster.ac.uk. And if you have any inquiries about GISMO, you can send them an email at gizmoenquiries@lancaster. And finally, you can look at the GISMO website, smartermaterials.org.uk. Thank you, and I can look at the chat if there are any questions.
Thanks, Alessio. That was fascinating. Yes, we do have a question in the chat already, and if anybody else has got one they'd like to do put it in the chat now. But we've had a question from Phil that says, can you provide some applications that the research is targeting or could be applied to?
Which part, Phil, are you referring to? I guess by the time was the first part, the one about the two-dimensional polymers.
Yeah, I think you're probably right there, yeah.
Okay, so these two-dimensional polymers are, let's say, can be used for catalysis because they can form these very nice order structures. Let me see if I can show you. They can form a perfect structure like this one that can selectively host molecules and thus can be used for catalyzing specific chemical reaction. Also, in particular, porphyrin can host metal atoms in the middle that are catalytically active. And in a research group, we are actually using some of these metal porphyrin that can catalyze polymerisation, such as catalyze reactions such as hydrogen evolution reaction, so production of hydrogen.
Okay, thank you. Phil has another question, in fact. You mentioned the double layer is most effective at 4 degrees. Does this mean that it loses its effect outside of this temperature, or is there a min-max temperature range application?
Oh, no. So it's effective at the range of temperature we tested from 37 to 4 degrees Celsius, which are, let's say, the most common temperature. So 37 degrees Celsius is the temperature of the human body, and 4 degrees Celsius is the temperature of fridge storage. It's just that it is more effective at 4 degrees Celsius with respect to the others.
Okay, thanks, Alessio. Phil, I hope that answers your question there. Alessio, you talked about some of the characterization techniques that you used, and clearly they've got a very specific, application in terms of your research. But are there any other areas of applicability, if you like, for those techniques in other areas of industry?
Oh yeah, of course. We have. Let's go back. So of course we have the XPS. We can, in general, be used to sense the surface chemistry. So it actually doesn't matter the material. We can look at the surface of each material, and I told you we can mill through the material. and look at the chemistry. So for example, if you have like maybe a painting or a coating on a surface, we can look at it, check the chemistry, check if everything is fine, try to look if it's changing throughout the material, and so on. While for the AFM, first we can use it to tell the morphology of your coating. So for example, maybe there are some, suppose you have a coating on the surface, maybe there are some cracks. We can check if there are cracks, and maybe this is reducing the effectiveness of the coatings, or we can scratch through the material to check how thick it is, or we can use the colloidal probe to check the chemistry of your material. So for example, I know people have used the colloidal probes to check the interaction with living cells or bacterial viruses. So you coat the tip with the fouling agent, and you check how it's interacting with the surface by approaching the tip to the surface.
James, if I can just add slightly to Alessia's answer as well, atomic force microscopy and scanning probe, sort of as the wider field of microscopies around that, are incredibly useful, and they're very versatile. So Alessia's talked about sort of the morphology and a bit about the chemistry, but you can also, because you're bringing a probe very close to your surface, you can sense various different forces. So you can maybe look at mechanical effects, thermal effects, electrical ones, magnetic, and so on. So it's a very customizable technique, and highly useful to pretty much anything where you've got, something solid that you want to look at and study, down to sort of nanoscale measurements.
Okay, Alex, thank you. Does anybody else have any questions for Alessio or Alex? Here we have another question incoming, I can see.
Okay.
Could this research be used on rubber?
I mean, if you're talking about plasma polymerization, I generally think so. So we can coat the rubber with the plasma polymerization. If you are talking about characterization, we can definitely use the XPS on rubber to check the composition of the rubber. And maybe we can even be able to do some AFM, but that depends on the roughness of the rubber. So if it's too rough, it might be difficult to scan it.
Okay. Phil, it sounds like there might be a useful conversation to have with Alex and Alessio afterwards on that one. Well, if just maybe give it another few seconds, see if there's any other questions.
I saw Martin raise his hand. I'm not sure if it was just by accident or he was actually going to ask a question.
I don't know if you can hear me.
Yeah.
There's no function on here for asking a question on my screen, so I can't. There's no chat box or there's no question box.
Go ahead and ask it.
I must admit that I know very, very little about your science, but I'm interested in the use of it. We're trying to coat a tube with something to give highly diffuse reflectivity of UV light, like PTFE or something like that. And we just wonder if you could comment on that a bit. Alex has given us some help on that, but it seems to be a challenging event process.
Yeah, so if you want to coat a large area product, I would definitely go for the plasma polymerization because it's easier to use. And I guess if you want to increase the UV reflectivity, you have to look for the right polymer with the right groups. Maybe the PTFE, I think also maybe it has some fluorine in it. can help, but can definitely look at some UV reflective coating, or we can try to add some metals, maybe, that can help reflect UV light.
Yeah, UV light does seem to have rather strange reflectivity characteristics, or I could have misunderstood that. As I said, my proficiency in this in this field is plus or minus 0. So
also, I think the thickness might be relevant. So the reflection of light might be dependent on the thickness of your material.
right.
So for something thicker could be helpful.
Yes, thanks.
Martin, just as a quick follow-up, I need to send you an update around the UV stuff anyway, so we can probably have a chat in the near future. I'm quite happy to involve Alessio as well if he wants to be there. But yeah, be good to catch up in the near future anyway.
Yeah, well, I know that I've been trying to get my head around enough information so that I can actually have a discussion and keep up. That's because it's not my area of expertise. I think you understand that, Alex.
Yeah, I mean, technically it's not mine, but part of the reason for these sessions and the things like the GISMO program is to try and help in these areas anyway. So yeah, I'll be in touch soon as soon as I get a little bit of free time to go through a couple of things.
Good man, that's great. That's great. Yeah, and hopefully we can maybe even take this further. So
yeah.
Mm-hmm.
Brilliant.
I would be happy to have a chat with you.
Yes, thank you.
Okay, good stuff. Well, as the chat clearly doesn't work for everybody, if anybody else has got any questions and they can't access chat, please do speak up now. Otherwise, we'll move on to the closing part of the webinar. Doesn't sound like it. Alessio, thank you so much for that. That was very informative, and it's I guess it's certainly taken Martin over and above plus or minus 0 this morning. So and I'm sure that has done for other people as well. So thank you so much for your talk today. Could you just move us on to the last set of slides? Oh, there we go.
Yeah.
Well, thanks very much. Good morning, everyone. My name's James Stancombe. I'm the program manager on the GISMO project, and very much like the last couple of minutes of the conversation, as Alex said, the GISMO program is here to help you with just those sorts of issues, and we can do so. We can help across a wide range of materials problems that firms face, or challenges that they face in developing new products and materials. We've talked today about being able to characterize the effectiveness of coatings. We've talked about antiviral and antimicrobial resistance, but there are other things that we can help with, all fully funded through the European Regional Development funded GISMO project, and that is to look at things such as material characteristics, to help you to look at new or alternative materials and methods of processing them. If environmental sustainability is key to your product, we can help you to look at how to improve in those areas. And if, for example, you need to look at the implications of a new design or formulation, we have extensive experience and can provide a lot of support in, for example, 3D printing and things of that nature. You may just want to benchmark the performance and characteristics of your product and materials with those of somebody else's, and we can very happily help with that. Or if you would like to think about how you can incorporate smart materials or smart properties into your materials and products, we're very happy to help you do that too. So if you have anything along those lines, please do get in touch. A slide or two from the end here will re-emphasize the contact details. Alessia, could you just move on to the next slide for me, please? Thanks. If you found it interesting today, then we'll blow your mind further on the 2nd of June and the 17th of June, when other graduate researchers on the GISMO project will talk about their research. So on the 2nd of June, Amy Crisp will look at methods to understand and prevent biofilm progression. On the 17th of June, Noah Wright will talk about frustrated Lewis pairs, hydrogenations, and their application in flow chemistry. And you can book on those events right now using the links shown.